Welcome to the Explainer. So, your network is up and running, but is it actually resilient? I mean, what happens when something fails? Today, we're diving into the protocols that act as your network's ultimate safety net. First, Hop Redundancy protocols. So, let's kick things off with a pretty critical question. Think about your own network for a second. It's got all these different parts, but there's almost always one weak spot, a single point of failure that can bring the whole thing crashing down. Any idea what it is? Yep, you guessed it. For most of us, it's the default gateway. It's basically the single door for all of your network's traffic trying to get to the outside world. And if that one router fails, well, that door slams shut. Your connection to the internet, to everything, is just gone, dead in the water. And we're not just talking about an inconvenience here. A failure like that is insanely expensive. Get this. According to a study, 98% of businesses say a single hour of downtime costs them over $100,000. $100,000. That is a staggering price to pay for what is essentially one single weak link in the chain. Okay, so how on earth do we fix this? How do we get rid of that single point of failure? The solution isn't as simple as just plugging in a second router. No, it's about creating a really clever technological illusion, what we call a virtual router. And that is where these things called First Hop Redundancy protocols, or FHRPs for short, come into play. They're a whole category of protocols designed to solve this exact problem. The goal? To let two or even more physical routers work together and pretend to be a single, super reliable gateway. So how does this whole magic trick work? Well, it's actually pretty brilliant. Instead of pointing all your computers and devices to a physical router's IP, you point them to a single virtual IP address. Now, behind the scenes, you have two or more physical routers listening on the network. One of them gets elected as the active router. It's the one doing all the work, handling all the traffic. The others, they just hang back in standby mode, waiting. The moment that active router goes down, one of the standby routers jumps in, takes over that same virtual IP, and becomes the new active one. And the best part? It happens so fast that your users won't notice a thing. It's totally seamless. Now, here's where it gets really interesting. There isn't just one way to pull this off. There are actually a few different protocols that do this, each with its own little quirks and features. Let's meet the three main contenders in the FHRP world. All right, you can see the key differences laid out right here. First up, you've got HSRP. That's Cisco's original, their own proprietary thing. Then there's VRRP, which is the big one. It's an open, industry standard, and that's super important if you're running a network with equipment from different vendors. And finally, we've got GLBP. This is another Cisco protocol, but it's kind of the next evolution. It doesn't just provide a backup, it actually load balances traffic across the gateways. You can also see they all use slightly different names for their router roles and even have their own unique virtual MAC address formats. Okay, so features on a spec sheet are one thing, but what really matters is how these things perform under pressure, right? When things actually go wrong. So how do they stack up in a real failure scenario? Let's dive into the data and see what happens. First up is convergence time, which is just a fancy way of saying how fast does the backup router take over when the main one fails. Now, with their out-of-the-box settings, things are kind of all over the place, but once you tweak the timers and optimize for speed, whoa. VRP just pulls way ahead. It becomes the clear winner, finishing a full failover in just 1.8 seconds. That's incredibly fast.
Okay, next up, packet loss. Because let's be honest, a super fast failover doesn't mean much if you drop a ton of data in the process, right? And this is where GLBP absolutely shines. Once you optimize it, it becomes the undisputed champion. It manages a perfect failover with, get this, zero packets lost. That's all thanks to its smarter load balancing design. Finally, let's talk about the cost. What's the hit on your router's CPU? Well, VRRP's incredible speed definitely comes at a price. It's the most CPU hungry of the bunch, especially once you've optimized it. HSRP also gets a bit more demanding. But then, look at GLBP. It's just the most efficient, hands down. And what's really wild is that its CPU usage actually goes down a tiny bit after it's tuned. Pretty surprising, right? All right, now for a really cool piece of insider knowledge about HSRP. Sometimes you'll see it fail over almost instantly, way faster than its configured timers should allow. So what's going on? Well, as Cisco's Peter Paluch points out, there's a special resign message.
Basically, when an active router is shut down gracefully, like by an admin, it sends out a little message to the backup that says, "Hey, I'm checking out. You need to take over right now." This completely bypasses the normal waiting period and makes the switch happen in a flash. Okay, so we've looked at the theory, we've looked at the hard data. Now for the big question. How do you take all of this and choose the right protocol for your network? Ultimately, it really just boils down to your specific situation. Let's break it down. If you're running an all Cisco shop and all you need is simple, reliable failover, HSRP is a fantastic, solid choice. If your network is a mix of gear from different vendors, well, you don't really have a choice. The open standard VRRP is the way you have to go for compatibility. But if you're on Cisco hardware and you want to squeeze every last drop of performance out of it by having both routers working all the time, then GLBP and its load balancing make it the undeniable performance king. And all of this leaves us with one final big picture question to think about. In today's world, network traffic is just exploding, and every bit of bandwidth is precious. So, is it really good enough anymore to have an expensive piece of hardware just sitting there idle, literally just waiting for something to break? Or is the true future of high availability a model where every single gateway is active, all the time, sharing the load and working together? The answer to that question is probably going to shape how we build reliable networks for years to come.